Okay, so what I'm going to try to do in my talk is to talk about the Rmatrix method with the idea, as applied to electromolecule scattering, with the idea of telling you how we use the method to try to ascertain where the uncertainties come from. Okay? So we'll talk about the basics of the method, what we can test, how we do it, and I will hopefully finish with some ideas on uncertainty determination. But the first thing I want to do is to remind people here, in particular myself, what the meeting is about. And the meeting is about uncertainties and not accuracy. We're very used to going to conferences and talking about how good our results are, how close to the true value, or if we don't have the true value, an experiment we trust. But here we are going to discuss uncertainties. So I'm going to try not to discuss how good my numbers are, not how accurate, but how precise they are. What is the uncertainty that these results have? Right. So what's the validity of the range of validity of the method? We use the Rmatrix method as applied to electromolecule scattering to calculate, basically, to solve the electronic part of the problem. So we work within the Born-Oppenheimer approximation. We solve a time-independent Schrödinger equation, and we assume the fixed nuclear approximation as well. The nuclei are held fixed during the scattering. So the method works best at low energies. We do not have states there that describe ionization. I will briefly mention our attempts at using pseudostates for this. We don't normally do calculations where the molecules have heavy atoms. We could, but I think they're computationally large. We, at the moment, can only include a few partial waves of the partial wave expansion in the calculation, so we do this ab initio for partial waves up to L equals 5. If high partial waves are needed because the cross-sections are not converged, then what we do is we go to a Born approximation and we use some Born correction. I'll mention that later. And on the whole, we calculate integral cross-sections. We can calculate differential cross-sections for elastic scattering. We can't at the moment for other processes. We could. It's not difficult. Other people do it, but we don't. We may do in the near future. Right. So what is it that we can calculate? Electronically elastic cross-sections. These in principle get poorer the higher the energy because of the channels that we're missing, particularly when we go above the ionization threshold. We calculate electronic excitation cross-sections. These are very dependent on the quality of the electronically excited states, and they're dependent on these in two ways. First, how good we can represent these in our calculations, but also how much we know about them. Because when we go to look at quantum chemistry calculations for this from the people that should know how to do this much better than us, sometimes there's virtually no data on electronically excited states for some molecules. Depends on the molecule. The other thing we do is to calculate resonance parameters, energies in width, and we just heard from Dan how these are used then to do calculations, for example, in dissociative electron attachment, and we will hear some more later on how we use these sort of data for other processes. We tried to calculate near threshold ionization cross-sections. We did for H3 plus and H2 using pseudostates. These, however, proved very, very hard and cumbersome because we have a lot of problems with linear dependence. We need to use orthogonal orbitals. I could go into this, it would be a whole talk. But on the whole, it didn't prove to be a very good way of going about getting near threshold ionization cross-sections. The pseudostates could be very powerful to do some other things for our calculations, but not ionization. And then, of course, we can use these electronic results, for example, K matrices, T matrices, to do other calculations for vibrational excitation, rotation excitation, so we feed our electronic data into other software. And Carol will talk about how we use some of the Rmatrix data, how he uses some of the Rmatrix data for other processes. Right, so we've heard about the Rmatrix method several times in this meeting, and some of you have heard about this hundreds of times, but I want to explain the basics because I want to explain what input we need and therefore try to ascertain where the certain uncertainty comes from. So the idea here is you split the space into an inner region and an outer region. It's in the inner region where the problem is complicated, exchange of correlations, which you need to describe accurately, and in the outer region things are in principle much simpler to do. And you have to define the boundary, there's a radius here, and the trick of the condition for the method to be valid is that all of the electronic density of those states that you want to consider has to be contained inside a sphere. Right, so basically we're trying to solve the time-independent Schrödinger equation, and what we're trying to do is to find this wave function, so we need to generate these wave functions and in principle determine some energy-dependent coefficients. In practice, we don't need those, unless you're interested in doing things like photoionization. If you want cross-sections, you don't need to determine those. All of the complication or the complexity is in finding that basis. And we expand that, as has been explained before. Dan mentioned it for the convariational method. Connor and other people talked about this for the electron atom scattering. We use this sort of close coupling approximation, and we solve to find these and the associated eigenvalues that are the Rmatrix poles. Now, most of the physics of the problem we want to solve is contained here, and therefore is the ingredients that put into this expression that will give us an idea, or could give us an idea of the uncertainty and the accuracy as well, in a way, of our problem. So what are the things, what are the ingredients that go in? These are wave functions that describe the target states that we want to go in. So how many of the target states we include and how accurate these are will give us an idea of the accuracy. Then these one particle functions describe the discretized electron, so the continuum electron inside the Rmatrix sphere. There are issues here as well with the quality of these, and I can talk about that a bit more. To a certain extent, this is something we should be able to converge on. So it shouldn't be a thing, a parameter in a way in terms of the quality of the calculation. And then the quality of the description of the short-range correlation and polarization is linked to these L-square functions. And again, how good we can represent correlation and polarization is important. So getting these right is also will give us an idea of the quality of our results. Of course, what we do is to obtain these coefficients, those coefficients, we diagonalize a Hamiltonian in the basis of some configuration state functions that are given by this product and those square functions. I'm not going to try to discuss neither what I think was called the epistemic uncertainties, i.e. those that are linked to the things we missed, nor the numerical ones. I think those are, many of those are not big enough, and some of those are probably unquantifiable in a way. And I think in any case, in our calculations, the bigger uncertainties come from the choice of the model. And that's what I'm going to discuss. Right. So the point here, and I'm not going to discuss the details, is that with all that inner region information and information about the target, we generate the Rmatrix elements, and these are going to give us the boundary conditions to solve a set of differential equations in the outer region. So in the outer region, the problem is simpler. We have a simpler expression for the wave function, and what we're aiming for is finding these, because we can link those directly to scattering data, k-vectors, data, etc. So to find those, we solve these self-coupled differential equations, and the thing I want to point out here is that we need these potentials. These potentials have an expression that seems complicated, but basically they're linked to the permanent and transition moments of the target, electronic targets involved in the calculation. So dipole moments, quadrupole moments, octupole moments in principle. In practice, we have dipoles there, quadrupoles at best, but we don't go beyond that. Right, so again, to solve those differential equations, we use various techniques. We use a propagation technique, in fact, we use asymptotic expansions, etc. This is the part where I think the numerical, we can test it, and I don't think the numerical uncertainties here are big enough. So this is not where the big uncertainties come from, I think. Right, so what I want to talk now is how we actually do the calculation and what input we need, and therefore to try again to work out where the uncertainties are. The first thing we need to do is to calculate the target property. So what we need is excitation thresholds. If we're looking at electronic excitation, we need dipole and quadrupole moments, as I said before. And what's the input that we require? A geometry, of course. We're not going to optimize the geometry for a molecule if that's available in the literature. A basis set, we have to choose how we generate some molecular orbitals for our wave function, and what type of configuration interaction model we are going to use for this. So all of these are inputs that we need to put into our calculation. Now, when we solve in the inner region, what we have to do is calculate these wave functions. the decision needs to be made as to how many electronic states are included in this calculation, what our matrix radius and continuum basis set we use, and these are linked, and what L-square functions we use. Some models, we've got some ideas, some prescription after if you use certain model, you put these L-square functions, but there's choices here. There are options as to how you do this. And of course, this is very much linked with sort of the approximation that we use. We don't tend to use an ecstatic exchange approximation for production runs for proper calculations, but we use both an ecstatic exchange plus polarization approximation, where basically only one electronic state, the ground state, goes into the closed coupling expansion, and that's described at Hartree-Fock level. Or we use closed coupling approximation, and we can put a large number of target states and pseudo states. I think we discussed before as to whether sometimes, it's been said several times, you would expect that the closed coupling method is more sophisticated, the approximation is more sophisticated, you would expect that it would give you better results. That's not always true. It depends, because it depends quite strongly on the ingredients that you put here. How we define better results, I don't know. Sometimes, of course, we look at experiment and do this. Sometimes we look at other calculations. So the input in the outer region is basically all of the above. So we use information from here and here. And then, of course, the propagation details, the details of how we solve the set of differential equations. Now, in practice, right, so as I said, sorry. In practice, as I said, the wave functions are used to generate a configuration interaction model. The molecular orbitals we use nowadays, we use an external quantum chemistry code, normally MOLPRO, to generate the orbitals, because we try to generate the wave functions at a class SCF level, which is particularly suitable if you're trying to reproduce electronically excited states. It's much better to do that. Because we need to use a single set of orbitals. So there's a choice. If you're using an SCP calculation, you're going to go normally for Hartree-Fock orbital. Otherwise, we generate class SCF orbitals. Now, all of these are choices we can make. And unfortunately, the quality of the scattering results is not linearly related to the choices we make. So a bigger basis set doesn't always necessarily give us better results. Why? Because a bigger basis set may give us perhaps better excitation thresholds, but a poorer dipole moment if the molecule has a dipole moment. A certain choice of states to include in the CAS-SCF calculation, the excited states to optimize, may give us better excitation thresholds for those states, but much worse excitation thresholds for other states, or a worse dipole moment. So it's not easy for us to see, depending on the molecule, which model, which combination of these characteristics gives us the best or the more accurate results, but that to a certain extent perhaps gives us a way of how to try and look at the uncertainty, the precision, by varying the models and looking how our scattering data varies with that. At the moment, so let me go back to this briefly, at the moment, these continuum orbitals that describe the scattering electron in the inner region are also expanded in the basis of Gaussian type orbitals. That's going to change. We're working very hard changing our codes and using B-splines for this, which we hope will allow us to improve, on some respects, the calculations quite significantly, actually. And again, as I was saying, the R-matrix radius, the use of GTO, sorry, let me just say this briefly, has to do with the fact that you can calculate the integrals analytically. It makes things much easier. Or you're trying to describe something as an oscillatory behavior with something that is centered, these GTOs are centered at the center of mass. So you get linear dependence problems very early on, and therefore we're restricted in terms of the size of the sphere that we can use, and therefore we're restricted in terms of the excited states we can describe. If we've got Rydberg state and water gas, fairly low-lying Rydberg state, we can't put those in properly, for example. So, as I say, the model, in a way, is defined by the basis set we choose, the type of molecular orbitals we choose, what configuration state functions we put in, or what active space if we're using CAS-SCF, for example. And we tend to choose these to describe accurately things like the ground state energy, dipole moment, electronic excitation energies, etc. Now, a lot of the things I'm going to show are for the clearing geometry only, working within the fixed nuclear approximation. But if you want to generate these data to, for example, calculate vibration excitation cross-sections, you need to do these for a number of geometries. And these, of course, makes matters more complicated because you need to ensure that the quality of your description is good, not just for a single geometry, but for a range of geometries. And I think to a certain extent, you need to make sure that the quality of that description is similar for all geometries, rather than that it's the best possible for each geometry, of course. Right, so the UK AMOL suite, which is the suite of molecular matrix codes, is freely available. This is in a repository. Anybody can download it. All you need to do is to register for it. It's great if people who know what they're doing try to use it, and normally they use it sensibly. It's terrible if people who don't know what they're doing use it, because indeed you can get pretty bad results, sorry. It's back. No, don't worry.
Why don't I make this a little bigger while I'm at it? Or at least put it higher. There we go.
Right, okay. So what this has allowed us to do as well is to make sure that the community of users, because there are people using these codes in several places, have a tool and a strategy to report back bugs and feature requests and so on and so forth. So what we're trying to do is to improve on the sort of verification side of the use, on the development of the software. I'm not going to go into the details of the programs. There's a number of modules that go into it. I don't think you want to know about this. I'm happy to talk about it in private if you want. So what I want to do now is to show you a number of examples of calculations that we have done, and to show you how the results vary with the model. Now, I have picked molecules that I don't think are of interest necessarily to this community. These are molecules of biological relevance. The reason why we look at those was mentioned by Dan. Now, I've picked these molecules for two reasons. First is because it's the targets we've been looking at in our group, in my group recently, so we've got experience with that. Second, these are big molecules. To an extent, I'm showing you the poorer results because we get better results the smaller, the molecules with fewer electrons. But it will give us an idea of the spread, of the certainty in the results, and also because they're harder to get right, we are already into the habit of publishing more than one cross-section, i.e. of putting into a published paper's cross-sections determined for more than one model. So this example is for pyrazine. So this is basically a benzene ring where two of the carbons have been replaced by nitrogen. This molecule has no dipole moment. And what we have here is 3 Rmatrix results and some Schrödinger results from Carl, Winston, Vince, McCoy. So the close coupling results are generated with 2 different basis sets. And in this case, we're using CF orbitals. The basis set varying that one has diffuse functions and the other one doesn't. And then we have an STP calculation. The close coupling results have around 38 electronic states included. The STP, of course, it only has 1. So what you can see here is that basically both close coupling results, so the red and the green curve, give very, very similar curves. Whereas the STP calculation, the STP Rmatrix calculation is quite different, particularly in this energy range, and it agrees much better with the Schwinger result. In this case, if I had to say which result is more accurate, I would be tempted to say this one. We also understand why the difference. It has to do with the description of the polarization and how this is done in the SCP and the close coupling results. But if I didn't have the Schwinger results, what I could say is that the uncertainty here is that big in the cross-section. The other thing I wanted to show is that you'll see that the SCP results have all of these peaks. I think people mentioned this before, these are pseudo-resonances. So these peaks are non-physical. They shouldn't be there. But in terms of getting the size of the cross-section here, they don't seem to affect very much the size of the cross-section because it's very similar to the results obtained with the close coupling method. It doesn't have that problem. Now let me move to a molecule with a dipole moment. Dipole moment gives us a headache, both to us and the experimentalists. So this is pyridine. So it's basically the same story, 2 nitrogens in the benzene ring, but instead of being in a way that there's no dipole moment, now there is a dipole moment of around 2 point something dpi. And so what we have here, if we concentrate here, is the same thing. This is the elastic cross-section. again, and there's two types of results. The black, the black and the blue line here are results obtained just for the Rmatrix calculation for the few partial waves that I said we can calculate at initial. Now we know the results are not converged in that case, so we use this Born approximation to basically include the partial waves that we cannot calculate at initial. This should in principle work relatively well. The higher the partial waves, the better the Born correction works. However, the dipole moment of this molecule is not small, and the bigger the dipole moment, the more problems there are for the approximation. But what I wanted to show here is, again, we've got Schwinger results. When we look at our matrix results and compare with the Schwinger results, they're green. The agreement is reasonable. There's, again, a problem here that might have to do with the description of the polarization, some difference. And all these curves fall within the error bars of the experiment. Now, these results we know are incorrect because they're incomplete. Our best results are those that contain the Born correction, contain all the partial waves. When we do that, we go very far from the experiment. Okay? However, the point is, we're doing something here less accurate with the Born correction, but experiment, and this was mentioned yesterday, has a problem with how they generate the cross sections. The measurements, and you can see these here, these are the differential cross sections. The measurements go down to, I think, 20 or 30 degrees. Below those angles, they have to extrapolate. They have to come up with an intelligent way of getting that cross-section, because they integrate these cross-sections to get that. When what we do is integrate our results in the angular range in which the experimentalists have got data, and integrate their results in their angular range, the agreement is this. So basically, these, I don't know if you can see them, but here are the points. So basically, we're clearly within the error bars. The problem for the polar molecules is what to do with the low angles. The experimentalists have a problem. We, in theory, have a problem in a way. I think we know. Yes?
Maybe I'm missing something. Shouldn't the low angles matter much less because of the same theta rating?
No, they don't, in a way, because the cross-section is so huge that even that doesn't. Yes. Yes. Yeah, you would think so, but it's still, a significant part of the cross-section, and I'll show that in the next. Yeah. I think I'll show that exactly in the next slide. Yes. So this is pyridine. You see a trend. We've studied all of these as in molecules. So here, the comparison. There's no experiment, but the comparison is. You see, I'm going to accuracy instead of uncertainty. I wanted to talk about uncertainties, and now I'm talking about the quality of the calculation. But let me just show you this. We're comparing some Schwinger multi-channel results from the group of Martin and Ortega. And what we have here, they have to do the same thing. They calculate the cross-sections for a certain number of partial waves, and they have to include those that they cannot put into the Schwinger method in some. They do it not on the cross-sections, and they do it on the amplitude. So it's a slightly different way of doing things, perhaps more accurate. So what we have is this. The uncorrected results, those that come from just the Schwinger multi-channel method and the Rmatrix method, are down here. So you can see the trend. In our case, we use different basis sets. These are all STP calculations, both the Schwinger and ours. There are differences that would allow us in principle to estimate an uncertainty. And when we correct the results, we go up here with our matrix calculation. The Schwinger multi-channel method goes there. Now, if you look at the differential cross-sections, the differences in the differential cross-sections, ignore these ones because these are not our matrix, but if you look here, here, and here, the differences in the differential cross-sections don't explain the differences. And the difference there comes from the fact that the Schwinger results, they've integrated within 1 degree and 180 degrees, because they were not confident in what the cross-section was below 1 degree. We didn't care, in a way, or perhaps we were a bit more ambitious and say we're going to integrate all angles. And in fact, if we don't, sorry, let me just say this, we don't generate the integral cross-sections by integrating the differential cross-sections. When you use this Born correction, you can just get it from one of the coefficients that you use. But if we do a numerical integration of our cross-section, from 1 to 180, we get back not exactly to here, but much, much lower. So it's that 1 degree that certainly in our calculation makes a huge, huge difference So we've got a problem here. We've got a problem of accuracy, but to a certain extent we've also got a problem of uncertainty. There's one thing I just want to go back and mention in the previous, or in this result, I think this will do. The cross-sections here are basically given by the border correction, or what you get at the border. So to an extent, whether you get your Rmatrix results within plus or minus 10%, I think has very little effect on the size of the cross-section in those low energies, actually. And this border correction depends very strongly on the data models. Now, whether, yeah.
So what's the stuff you go in making your Rmatrix calculation for the higher partial waves? Are you just out of computer for it? Or is the representation of those high L's?
The truth is that in the current code we can't, because the way the program is coded, we cannot go higher than N equals 5. You need some coefficients that have normalization coefficients for spherical harmonics, and that those numbers are putting up to N equals 5. And we're also using a very old quantum chemistry code that has no comments in it. We tried to change it. No. It's something, it was the Sweden molecular code. So that's what calculates our integrals. You go into the code, we wanted to change it, there's no comments at all, you have no idea. All of the sizes, all of the vectors are hard coding, and you have no idea. Now Connor's going to tell me he did it.
No. I'm just bringing up, just following on from what Jim said yesterday. So they do that in time-dependent methods where they go up to a particular L value. Now they try to match the distorted wave for that and say, so could you not do the same for maybe the L equal 5? See what is the contribution from the Rmatrix, what is the contribution from the Born, and maybe scale your Born cross sections for the higher L based on that?
I don't think there's any evidence there's a problem. I don't think there's a point in a lot of work improving the high L Born corrections. There's no real evidence there's a problem. So I think they still have a dimension point, because maybe you have a problem between 5 and 10, not at 5.
Yeah, but so are you saying that the Born at L equals 6 would be pretty much the same as the Rmatrix?
You can test that very easily.
We have done, I suspect you've done, where you changed 4 to 5.
We do this regularly.
And I haven't seen a big difference.
No, we do this regularly, and if it's not in any of the results I've shown so far, it will be one of the results I hopefully eventually show. Yeah. So you look at, you can see it here. Compact basis set with L equals 4, compact basis set with L equals 5. So the blue and the purple line there, in fact, are Born corrected, but where the L is different. Yeah, so there is a difference. There's a small difference. Okay? So if you want, in this calculation, the Born correction starts in a partial wave L equals 4, and this one in the L equals 5 and L equals 6. And we can see some differences, but no.
So that's 2 curves, right?
These two, the purple and the blue there, okay? So you see that there are some differences here, but you've got a lot of pseudo resonances here, so, I wouldn't look at the shape, I wouldn't be so, I wouldn't look in so much detail in that region. Now, in the code, we're redeveloping the code to one of the things we want to do is to be able to use more partial waves. For, not necessarily for this problem, but for other problems, particularly if we want to use the inner region to treat molecules in intense laser fields, and then you need higher partial waves. So we will get there, hopefully, soon.
Were you able to identify
Sorry?
of each of these resonances?
So the non-physical ones, no, because they're non-physical.
They are not physical.
No, the pseudo resonances, they're non-physical. They're a limitation of the way we expand the wave function, because you have a mismatch between the natural region. The resonances that are physical, and we actually studied these systems to look at the resonances are here, and here, and here. And these, yes, we've looked at, studied at nauseam, basically. Right, so I'm going to go to electronic excitation, if I've got time. And I think the problem here is even worse. And I'm going to start with an example of water. It's an unfair, it's a quite detailed example because it's state-to-state electronic excitation. And there are a number of curves and points here. The most recent experiments are in red dots, and those are experiments from Mutigaku and his group. The squares are some measurements from the mid-2000s from Penny Thorne, so it's the people in Australia, Michael Brander, and people in Japan. And I think these people were re-evaluating these results, not the measurements, but how we analyzed them. And then there's quite a bit of theory here. These pictures are from a paper from Anurel and Tony Racine, published in 2013. I think their results are the full lines. The green lines are the more recent Rmatrix results. They were done by me in 2000. There's some earlier Rmatrix results from Leslie Morgan that are fairly different from my Rmatrix results. I could explain why that is. And the red lines are Schwinger results from Carl Winston, Vince, McCoy. So what I think you can see is there is quite a spread here still. But on the positive side, my feeling is that there are sufficient methods, there are sufficient calculations that we could look at using that spread to determine an uncertainty for our electronic excitation cross sections. The other thing, I'm going to show you some more electronic excitation cross sections. Going back again to one of these big molecules, if it lets me. No?
Up there, what are you trying to do? What are you trying to do?
Just go down.
Just go down.
Yep.
Oh dear.
I think it's just...
It's right here. You just gotta click it.
Okay.
And then
Okay.
do that.
Yeah, okay, thanks very much. So there's two things I want to show you here very briefly, because I suspect I'm running out of time. In this case, there are some experiments as well. This is, again, pyrimidine, a much more complicated molecule. The experiments here are very complicated. They've got to deconvolute their electromolecule loss, and they've got to do that by using spectroscopy data to see where the excited states are. So there's there's quite a lot of uncertainty in the experiment. We again do a number of calculations. We use the bond correction when needed, and we get a difference of about 50% in the cross-section depending on the basis set that we use. Now, one of the things that I said before is that one of the input parameters that go in is the excitation thresholds. Okay? So we could say, okay, let's see, we do our calculation, we put some excitation thresholds that are consistent with the target wave functions that we use. Okay? Now, we know that these excitation thresholds are poor, but we can go to the literature and look at excitation thresholds produced with much more accurate quantum chemistry methods. And we can say, okay, in the input for the outer region calculation, we will replace our excitation threshold with the more accurate excitation threshold. If we do that, in this particular case, because there are a lot of excited states in this energy range, you basically go from this line to that line. So the difference between those two curves in no way gives you the uncertainty of your calculated cross-section, I think. I believe that the experiment is here. I believe the experiment is not very accurate, but our calculations are probably not very accurate either. And using just one set of parameters to try to determine the uncertainty, I don't think is good enough. Right. I'm not going to tell you there's more testing that we can do. With these bigger molecules that I've shown you, we publish this data. We publish data for STP and cross-coupling calculations for two different basis sets. So although we are not quantifying the uncertainty, we're implicitly telling people that read the papers, well, you know, whatever difference there is between these curves, this is the minimum uncertainty that we have in our results. We don't tend to do it for smaller systems because for smaller molecules it's easier perhaps to say this is probably our best model. But we can do it because we do it in a way. We do these tests before we come to decide these are the best results. So this is some example for our smaller system, formic acid, where we change number of states, basis set, etc., and we see how things change. Now, one thing to point out here, when you've got a resonance, the problem is that a relatively small shift in the resonance can change the size of your cross-section for a certain energy quite a lot. And if we're trying to provide uncertainties for cross-sections for different energies, we need to take that into account. Now, let me finish with some ideas. I think because we already do it with the Rmatrix and I suspect with other methods, we can perhaps run a number of different calculations within the same method and look to see how the output, the scattering results vary with this input. And there's two things, for example. With the target properties, there are explicit dependencies. That is, we put the value of the dipole moment as an input for the outer region calculation. We can vary that, and we can see how the results change. However, we also put in some electronic wave functions. And it's not obvious how, you can't change those systematically, because this depends on the configurations, the basis, how you diagonal, what comes out of the diagonalization of the Hamiltonian. So it's harder, perhaps, to determine the dependence on the implicit quality of your target description. But the question is whether you could look at some outputs from that. Okay, you've got some wave functions describing to your excited state. You look at the energies that produces. Does that give you a reasonable idea of the quality, perhaps, of those wave functions? I think I've said this before. We do this in the matrix calculations. If nuclear motion is involved, if we're going to provide these for nuclear motion calculations, we need to find a way to assess how the quality varies with geometry. If we don't want to do this for every molecule that we run, or as I say, we do it a little bit, we could perhaps try to look at some benchmark systems. But I'm worried about this. I'm a bit concerned because unless the molecules belong to a very clear family where they're very similar, I think it's difficult to extrapolate that if a change of a basis set for a molecule like water gives you a difference of 10% if you cross-section, the same change in basis set will give you the same type of difference in a molecule that is completely different. Because if you're looking, for example, at electronic excitation, the excited states may be very different. Some of them may be Rmatrix, some of them not. You may have a much higher density of excited states. So we've got to be careful if we want to use some sort of benchmark systems for that. And we would have to decide how many and what to pick. Now, the other question I've got, and I don't know about this, is whether trying to determine uncertainties for certain cross-sections is more valuable or more necessary than for some other cross-sections. And let me just say that we could compare between methods. And I was talking to Marco yesterday, who told me that this was actually done 30 years ago for H2. Perhaps this is something that we need to revisit now. We've all improved our codes and our methodology, and we could probably look at some molecules to do this. For elastic scattering, I think this is easier, and we could pick really an identical model. We've got to be careful, because sometimes my SCP is not your SCP. We sometimes think that we're doing the same thing when in fact we're not. But if we talk about it, we could actually pick an exact same model, and then look at the differences, if indeed there are any, and say that that is perhaps our method uncertainty. With electronically inelastic scattering, it's not that there are fewer methods, it's that there are fewer results, because the calculations are more complicated, and I think people are more reluctant, I think, to embark in those calculations. But we could again choose a number of benchmark systems, use the same level of approximation. There's an issue as to whether we use the knowledge of strengths and weaknesses in the method. I think we know that certain methods work better for certain things, can do certain description of certain processes better. We may want to use that. We may end up arguing, your method is better than mine, or my method is better than yours, and not get anywhere there. But I think we need to do it, probably, if we want to use the data to determine an uncertainty. And as I was saying before, we need to look at the resonance positions, because these can change the size of the cross-section very much. So perhaps it's not just an uncertainty in the cross-section we need to deal with, an uncertainty in the energy, in the value, that cross-section corresponds to which energy value. Finally, and I've not talked about this very much, we don't have a method that allows us to calculate all of the cross-sections in one. So if we want consistency, if we want to see that all the different cross-sections add up to the total cross-section, they may or they may not, and that might or might not help us to give some idea of uncertainty. Of course, it would tell us if the uncertainties are too small, because if we are very, if we give uncertainties that are very small cross-sections, and the sum of our uncertainties doesn't add up to the difference between the sum of the cross-sections and the total cross-section, then clearly we're doing that wrong. Right, and I get to the end of my talk. I just wanted to mention that there are a lot of people that have contributed to the development of the electron-molecule matrix method. Many of them are in the room, and the results that I presented have been calculated both at the Open University and UCL. All of these pyridine, pyridine results are from my current postdoc study, which has been doing a lot of good work on that. Thank you.